Good morning, everyone. My name is Maria Diaz, and today I'm going to talk to you about the characteristic polynomial of a spread in FQ4. We will begin by setting some basic notations. A finite field of order Q will be denoted as FQ. The set of all n by n matrices with entries in my finite field will be denoted as M and Q. And a k-dimensional vector space over FQ will be denoted by FQ to the k power. Now we're going to go ahead and give the definition of spread. A spread of a vector space FQ4 is a set of two-dimensional subspaces of FQ4 that intersect trivially and also partition the non-zero vectors of FQ4. Particularly, if S is a spread of FQ4, then the subspaces of FQ4 that are elements in S are called the components of S. All right, for the sake of our presentation, we're going to focus on the spreads that look of the following form as we have in front of us. For Q odd and theta non-square elements in FQ, then we consider the set of matrices of the form xy, theta, yx for all x and y in my finite field. M determines a so-called continuous spread of FQ4. And since M is a field, then M also determines a regular spread of FQ4. If you recall back from the definition of spread, a spread is basically a set of two-dimensional subspaces, right, in my vector space FQ4. Now here, we're looking at the set of matrices, and that is because we can actually associate some of these two-dimensional subspaces with matrices. Okay, so now that we have our object of focus, we're going to continue by defining a new geometric object. So regulus. In a four-dimensional space, a regulus R is the set of Q plus 1 components of a spread that pairwise intersect only at the zero vector, such that there exists Q plus 1 other components of a different spread that also pairwise intersect only at the zero vector and cover the same vectors. Now, the set of all of these Q plus 1 transversals of R is called the opposite regulus R prime, most commonly known as a derived regulus of R. Now, we're going to be using this regulus object within our Knuth spread to create new spreads. So let's go ahead and begin. In the Knuth spread, we can consider the Q minus 1 disjoint reguli represented as the following. So for each K in my multiplicative group FQ star, we're going to consider the set of matrices RK that look like TU, theta U, T, where the determinant is exactly K. And its opposite regulus is going to be RK prime, which is a set of matrices RS, negative theta S, negative R, where the negative of the determinant is going to be K. All right. Now let's construct our new spreads. We let S be the Knuth spread as defined above. For some K multiplicative group FQ star, we consider reguli RK and RK prime as defined previously. Then by construction, we can see that RK is actually a subset of S. If we take out RK out of S and replace it with its derived reguli, RK prime, we have that's also going to be a spread of FQ4. And we're going to see that that's what's going to happen if you do multiple regular replacements. Okay, so now that we have our spreads of interest, we're going to continue by defining now a characteristic polynomial. We let n be a matrix M and Q. Then we have our characteristic function of with respect to n that goes from the set of matrices to my finite field. You take a matrix M and then you compare it to n. If M is exactly n, you get an output of 1. If M is not n, you get an output of 0. So naturally, when you take a set S in the set of matrices M and Q, then my characteristic function over the set of matrices is just going to be a sum of the iterations of all the matrices in S. Okay, so where does the polynomial come in place? It comes in place because over a finite field, we can write any function as a polynomial. And thus we can write the characteristic function that we define above here as a polynomial. Okay, so why do we care about this and what is the focus? In 1997, Libler proposed that this polynomial could be used to study the structure of spreads of FQ4. Particularly for us, we're focusing on the spread where we do regular replacements within the Knuth spread of FQ4. So here we're taking the characteristic polynomial over the spread where we did one regular replacement. And because of properties of the characteristic function and the set S, RK prime and RK, we can actually write it in this way. Okay, so what is known? In 1997, Wilbur proposed that for S being a spread of FQ4, then the degree of the characteristic polynomial is going to be 2 times Q minus 1 when S is a regular spread. Now, when S is a whole spread, then the degree of the characteristic polynomial of that spread is going to be 4Q minus 6. Moreover, a professor here at Fresno State, Dr. Vega, came up with this result that says when S is a spread of FQ4, any type of spread, regular, whole, doesn't matter, then the degree is going to be bounded by 2Q minus 1 and 4Q minus 6. So this is a generalization of Libler's theorem. So with this in mind, a question about the degree of the characteristic polynomial of a spread obtained by multiple regular replacements arises. So here, now I give a new example where it's a characteristic polynomial over a spread where you do 2 regular replacements. And thus we can see that you can write it this way. And moreover, this difference is going to keep showing up more and more as we continue to increase the number of regular replacements. So because the difference is going to keep showing up, it is important for us to study it. And that's exactly what we did. Okay, so some known results. I'm going to go ahead and present it to you for Q equals 3. So when K is an F3 star, then we consider my difference for any arbitrary matrix. For simplicity, I will use the notation Fk to be equal to this difference. So we have looked at this difference can actually be written as the following polynomial. And through the use of a software called Sage, then we can actually rewrite it in this cleaner form. Now, let's say we want to consider the spread obtained by replacing one regulus, okay? And remember, we're still looking at when Q equals 3. So we're looking at the degree of the polynomial that looks like chi of S plus chi of RK1 prime minus chi of RK1, right? So we already have a form from this, as I showed you previously. And it looks something like this, all right? So now by taking possible values of K1, we analyze the degree. We only have 2 possible values in F3 star. That is 1 and -1. When K1 is equal to 1, it must be the case that the degree is going to be 6. When K1 is equal to -1, it's also the case that the degree is going to be 6. Note that for any possible case that you take of K1, when it's in F3 star, you're going to get the degree of 3 times 3 minus 1, which is exactly 3 times Q minus 1. And this is important because later on, I'm going to go ahead and show you a claim and a conclusion that we get when it comes to the degree of 3 times Q minus 1. So by exploring the cases Q equals 3, 5, and 7, we get that for any K in my FQ star, my difference or my FK has only an even degree that will range between 4Q minus 6 and 3 times Q minus 1. Moreover, it's going to have the structure of a polynomial in K, where you're going to see that it's going to look like this. And O of 3 times Q minus 1 minus 2 represents an expression of degree at most 3 times Q minus 1 minus 2. So we were able to generalize this and prove that actually it is true. It will only have terms of even degree, not only for Q equals 3, 5, or 7, but actually for any Q when it is an odd prime. Okay, so I'm going to go ahead and go over my conclusions. There was actually enough evidence provided to claim that the common constant factor of all terms of degree 3 times Q minus 1 in a K will be K to the Q minus 1 over 2. But for now, we're going to leave that as an open problem. And also, we're going to leave as an open problem the claim that the degree of the characteristic polynomial of a spread obtained by regular replacements will be bounded from below by 3 times Q minus 1. Thank you to everyone that came to this talk. Special thanks to my mentor, Dr. Vega. And like Victor E. Bulldog said, algebra is the glue that brings all mathematics together.